So, welcome. This is going to be the last lecture on in this MIP star equals RE trilogy, and it's going to be the it's going to be like the culmination of the last few lectures, where we see what goes into proving this compression theorem that we described last week. But really, it's not just the culmination of this these last few lectures, but in some sense, it's kind of the culmination of this class. I mean, it's the second to last lecture, but I really view it as where so many of the things that we've talked about in over the last 10, 11 weeks really come together. So just like in movies that we've seen, like in Lord of the Rings or something, characters that were introduced early on in the movies or in the series make an appearance at the very end, at very convenient times. For some important plot device, this will happen in a very similar way. So a lot of the ideas and concepts that we've seen starting from lecture 1 and onwards will make an appearance today. With that, let's jump into it. Any questions before I begin?
I kind of had a question.
Yeah.
I was reviewing the notes again before, earlier today. I just want to check if I'm misunderstanding something. So we have this sequence of games G sub n, and they're kind of defined recursively. We never really defined like a sort of base case, did we? Like, I don't understand what any of the games actually are. Just I know what one game is if I know what the next game is.
Mm-hmm. Well, so the games are not recursive in that sense. So in the lecture notes, if you open them up, and actually maybe I'll just pull it up on the screen so we can all see it. So let's see. So if we look at the description of the sequence of games, these ones, right? G sub n. So all of these steps here are well-defined by themselves. I mean, certainly step 1 is well-defined because we fixed the Turing machine M. This compression procedure C is also a well-defined thing because that's what the compression theorem guarantees us. The Turing machine V, this is maybe this is the only self-referential part of the description because V is the thing that defines the sequence. But kind of like I tried to hand wavily justify last time, this is an okay thing to do. Like a Turing machine can invoke its own description. So all the Turing machines here are well defined. M, C, and V, they exist. And here in what this this game Gn is going to do, it's going to call the Turing machine V, it's going to compress the Turing machine V to get this V prime, and then it's going to run V prime on some index n+1.
I guess maybe my question is, have we constructed V explicitly? Are you saying like, should I take this as an explicit description of V?
Yes. So yes, this whole description, this block here is a description of V.
Right, because I'm not seeing like anywhere where you would have, in this description, a description of any actual game the way we defined it in terms of like, questions and possible responses.
Oh, I see. Right. So okay. So there needs to be a translation from this description here into a formally like a game where you, right, you specify a question distribution, and also you specify the decision procedure. So you do need to like factor into these two pieces. You're right about that. But it is explicitly contained in this block of this algorithm block here. Yeah,
okay.
that's a good question. Yeah. Other questions? Okay, so let's go to, yeah, let's review what this compression theorem that we discussed last time. And we saw how using this compression theorem, you can define this sequence of games G sub n, which encode whether a given Turing machine M halts or does not halt. So clearly this compression theorem is a very powerful device. And so we want to see what goes on inside of it. So this lecture, we're going to prove the compression theorem, or rather we're going to prove a simpler version of it. It's kind of like a baby version, but it still has all the main ideas of the proof. So here's the baby version. There's going to be a couple of simplifications. So, what does it say? It says that there exists a compression procedure in algorithm, which we call C, and it maps uniform game sequences to uniform game sequences, right? Just like last time. And what does it do? It says, suppose that you walked up with a game sequence G, G1, G2, G3, and so on. And last time I said that this input game sequence is polynomial time computable. In fact, we actually have to assume something a little stronger than that. And I updated the notes to reflect this. And it's not so important for our discussions, but just so you know, we're going to assume that, in fact, each of the games are computable in n squared time, where n is the index of the game, where Gn is computable in O of n squared time.
Is n squared really matters, or the goal here was like to reverse the order of the, it's not like for all games there exists a polynomial, but there exists a polynomial for all games.
Exactly. Yeah, it's just to specify some concrete time bound for all of the games. Yeah. So I just picked n squared because it's like a convenient thing. It doesn't have to be this. So you assume it's all these games are computable in this time, and what do I mean computable? I just mean that the verifier in each of these games takes that much time to sample the questions and compute its decision procedure. So you assume you get as an input this game sequence. Then when you compress, you're going to get a new game sequence G prime, right? So we get a bunch of these compressed games. And here I'm going to like do the indexing a little differently than last time because it'll just be more convenient for what we're going to discuss today. So what's the relationship between the G primes and the original Gs? Well, we have what we call the yes case. If the quantum value of the original game Gn is equal to 1, then this compressed game, Gn prime, so before we had, we went from n to n plus 1, Here, we're just going to keep it n between the g and g prime. So the compressed game also has value 1. And in the no case, if omega star gn is less than 1, then the compressed game also has value that's less than 1. And here is this last bullet point is going to justify why we call it a compression theorem, which is that the complexity of gn prime, this compressed game, is polylogarithmic in n. Okay, so this is going to be, notice that this is much, much smaller than n squared. Okay. And so this is why it's called the compression theorem, because this game, gn prime is much more compact than the original game gn. So it looks very similar to the compression theorem we discussed last time, but there's a few differences. One, we no longer talk about this entanglement lower bound, just because we want to keep things simple. And here, there's another crucial difference is that we're not going to care about, we just basically want to preserve in this compression whether the original game had quantum value 1 or not. Okay, so it's, the yes case is value 1 and the no case is value less than 1. Hopefully that makes sense and looks familiar. Okay, so what's the, the high level idea behind proving this compression theorem? So the thing to note is, imagine for a moment that we didn't have this third bullet, right? So we only had, the first two conditions on the compressed game. Then this theorem would be completely trivial, right? So can someone tell us why?
The same games.
Sorry?
Yeah.
You say that again, Yuval?
Oh, just output the same games.
Exactly, right? You can let G prime N be exactly Gn, right? And of course, since they're the same, the first two bullet points will be satisfied. So clearly the non-trivial thing is that somehow we've reduced the complexity of the game. Okay, so we're going to reduce the complexity of the games in two steps, right? Right. So what goes into the complexity of the game? Well, the first thing is the verifier has to spend some time generating the questions somehow. And it generates the questions, the player provides their answers. Then the verifier has to compute the decision procedure. So that's the second source of complexity. And what the verifier now wants to do is it says, I'm too lazy to do any of these things. Instead, I want to make the players do all of these computations for me. I'm going to offload the work, but I'm going to check that the players are doing this offloaded work in a proper way. And I'll do all of this in a way that's much more efficient than if I did the computations myself originally. And to do so, it's going to use a bunch of things that like I said, we've seen before. One is this, it's going to use the rigidity of some non-local games. It's going to use ideas from this verification of computations that we saw a few lectures ago. It's going to use the uncertainty principle. And it's going to use PCPs, probabilistically checkable proofs. Not the quantum kind, because that's still a conjecture, but the classical kind, in fact. And these are the main ingredients that go into this compression. Okay, so let's see. So we can sort of think of what in this compressed game, this G prime N, what we can, this picture we should carry around in our head is that the verifier is going to play some protocol with Alice and Bob, right? Ask some questions and get some answers back in a way that forces the players to be essentially simulating the interaction between the verifier and Alice and Bob in the game GN. Okay, and we'll make this cartoon picture precise. Like, what do I mean? But this is sort of like the picture to keep in mind. Okay, so this is the compressed game, and this is the original game. There are two steps to this, and we'll basically break up this lecture into these two steps. The first step is called question reduction. And the second step is called answer reduction. So in question reduction, the verifier is going to focus on reducing the complexity of sampling the questions. So we're going to reduce complexity of sampling questions. Originally, it was n squared, right? Because that's what we're assuming is the sampling complexity of Gn, the original game. We're going to reduce it from n squared to polylog n. Right. The decision complexity will remain the same. It'll stay n squared or thereabouts. Okay. And then in the answer reduction, we're going to reduce the complexity of the decision procedure. Again, from n squared to polylog n. Okay, so let's start with the question reduction. How does it work?
Like, do you plan to like ask shorter questions, or are you going to force the provers to create randomness for you?
Both.
Okay.
Yeah, that's a good question. So you're alluding to what we'll get to. So it definitely, in order for the complexity of, say, the sampling to be smaller, that must mean we're asking shorter questions, right? The questions can be at most polylog n bits long. Because that's, you need at least that much time to output those questions. So in question reduction, we're going to take advantage of rigidity. And basically, so instead of, so in the original game GN, so I'm going to call it in the original game OG, GN, what is the verifier doing? It's somehow sampling a pair of questions X and Y from this distribution mu sub n. Right. But now it wants the players to do this for the verifier. And let's just take the simplest possible case where this distribution mu n is the uniform distribution. Right. And let's imagine that it's the uniform distribution over n-bit strings. So in the game GN, Alice receives a uniformly random n-bit string. Bob also receives a uniformly random n-bit string that's independent of Alice's string. So now our task is to somehow get Alice and Bob to sample from this simple uniform distribution, right? And we can use a non-local game to certify that they're actually generating uniform randomness. Okay, so here's a warm up. Let's put aside this game GN and G prime n for now. Let's just put it aside, and let's think about the magic square game that we talked about before. So imagine that you as the verifier, you're playing Magic Square with the Alice and Bob, and they're playing, and they win with probability 1, or maybe close to it. Since the game is rigid, you know that up to local isometries, these two players must share 2 EPR pairs, and they must be performing polyobservables on their EPR pairs. Right. So they win with probability close to 1. By rigidity, Alice and Bob, they must be sharing 2 EPR pairs. And they're going to perform these poly measurements that are specified by this, this 3x3 grid, right? Grid of observables. So we saw this a few lectures ago. And I'll just write down the operator solution again. So we had XX, XZ, ZX, YY. And remember that the way we described the Magic Square game before, Alice was the constraint player, meaning that she received a row or a column, right, and a constraint in this Magic Square game. and Bob was the variable player. Like he received one of the 9 squares as his question. And when Alice gets, let's say she gets the first column as her question, she's going to measure these 3 observables on her 2 EPR qubits. And when Bob receives a particular square, let's say the middle square, he's going to measure that observable on his EPR qubits. Actually, what will be very useful for us is for us to consider a symmetrized version of the magic square game. And by that I mean the role of who's playing the constraint player and who's playing the variable player can switch between Alice and Bob. So sometimes we'll ask Alice to be the variable player and Bob to be the constraint player, meaning that Alice will just get a single square and Bob will get a row or a column, right? And by symmetry, it should be easy to convince yourself that it really doesn't matter who's the constraint and who's the variable player. And we just randomly choose at the beginning of the game. Okay, so we'll just consider this variant of the magic square game. It's a little more symmetric between the players. And it's not hard to see that this game is essentially equivalent to the game we had before. Has quantum value 1, and it has the same exact rigidity properties. And the reason this will be useful for us is because we want each player to equally expect, like they should each be able to get a single square as a question, right? Okay, so hopefully this makes sense. Just like a slight change to the definition of our magic square game. So given this symmetrized magic square, we're going to do something similar to this Grillo verification protocol. So if you remember there, what did we do? We used this magic square game or many parallel repetitions of it as a subgame. And the reason we did this is because we wanted to ensure that the players were doing measurements when we wanted them to, right? So imagine that, so let's consider the following game. So with probability 1/2, perform one of 2 tests. So the first one is called the rigidity test, right? And this is where we just play the symmetrized magic square. Okay. The other test that we will perform, we'll call it the sampling test. And here we're going to tell both players to be a variable player. And we're going to tell them to report the value of the first square, which is the one in the top left corner. So tell. Okay, so when they get this, when they both get this single square question, they'll respond with just a single bit, right? And what the verifier will do in this case is accept if their bits are equal. Okay, so suppose they win this, this concatenated game, these two games together with probability that's say close to 1. What can we deduce about their answers in this sampling test, the second test? Any ideas?
Won't they both output the same answer, and that answer will be a random bit?
Perfect. So, how do you deduce that?
So when you apply the IZ operator to their entangled state, the identity operator doesn't do anything, but the Z operator will either give a +1 or -1. And you know that because they share the maximally entangled state, when they both perform this measurement, they're both going to get the same thing. And so they randomly both get a +1 or randomly both get a -1.
Exactly. And how did you know that they actually had this maximally entangled state or were performing this IZ measurement?
Well, if we happen to give them the rigidity test, then they would have to have done this these kinds of measurements. And because we are assuming they win with almost 1 probability, that means they have to be accounting for this case as well as the sampling test case. They don't know which test they're in.
Perfect. That's exactly right. So the key thing is that from each individual player's point of view, they have no idea whether they're in the rigidity test or the sampling test. So if they want to win well overall, they have to do well individually in each test. And since we know that the symmetric magic square game is rigid, we know that they must be doing this honest strategy specified by this grid up here. And they must be using EPR pairs. So when we tell them to both measure this top left square, they're both going to measure their 2 qubits using IZ. This is equivalent to just measuring the second qubit in the standard basis. And we know that what happens when you do that with the EPR pair, you're going to get uniformly random but matching outcomes. Okay, so let's write that down. If the players
probably only requires a minor modification, but just looking at these 2 tests, wouldn't the very fact that they're getting a question about the top left corner tell them that they're very likely in the sampling test?
I guess from their point of view, it's maybe more likely, but there's still at least some, I don't know, I think it's 1/9 chance or 1/18 chance that they're in the rigidity test. And so if they want to win with, let's say they want to win with probability 1, then they can't afford to mess up to deviate even on that, that small chance.
Yeah.
Yeah, good question. So probably 1 or extremely close to it. Their answers in sampling test must be uniformly random. Okay. So this is kind of cool. This, by using rigidity, we can actually certify that players are generating uniform randomness, right? And this will be like the basis for our question reduction, because we can say, hey, you've generated this randomness. Why don't you start using this randomness and treat it as if it were your question in the original game, GN. But we're not quite there yet. There's still a bunch of issues. One issue is that here we're only generating one bit of randomness, right? Whereas in this question distribution mu n, we actually wanted n bits of randomness. That's not such a big problem because, for example, you could just repeat this n times. But just repeating this naive protocol n times wouldn't be good enough for us. Anyone see why? Off the top of your head.
Is it a problem that they both see the entire question string?
That is a big problem. I haven't even got there yet, but yes, you're right. I mean, here they're getting matching question bits, question strings, right? So that's not so useful for us. But even before that, there's some kind of, there's some issue with, say, repeating this n times in parallel.
Don't we want the complexity to be log of, or poly of log of n? So if we repeat it n times, that would violate that?
Yeah, that wouldn't be a very efficient sampling protocol. Like the amount of randomness that the verifier is investing into this rigidity and sampling test is already more than n, right? So it doesn't seem so useful. So first we'll need to be more randomness efficient. So we're going to use a more sophisticated rigidity test here. No, this is not a good color. And this will, this rigidity test is called the quantum low degree test. I'll abbreviate it by QLD. And this was first developed by Natarajan and Vidic, 2018, thereabouts. And what this test is, it's an infinite family of non-local games. So QLD1, QLD2, and so on, where for each n, QLDn, it's itself a non-local game, and it has complexity polylog n, so that's the thing we wanted. And it has the rigidity properties that we want. So it has value, quantum value 1. And it's a rigid game. And its optimal, unique optimal strategy has the following properties. If they're winning with probability 1, the two players, Alice and Bob, have to share n EPR pairs. And in this game, Alice and Bob are getting asked all sorts of different questions, but in particular, there are two special questions. Two special questions that we'll take advantage of. One is called total Z, and the other is called total X. And when each of them get, say, the total Z question, in the strategy, what they're going to do is to measure each of their n qubits in the standard basis.
this.
And in total X, they're going to just do the same thing, but all in the X spaces. So for each of these two special questions, they're going to return n-bit strings. Right, and in particular, they're going to be uniformly random strings because that's what happens when you measure n EPR pairs in either the Z or X spaces. So this is going to be the our base rigidity test. It's like magic square, except it certifies n EPR pairs, but with very, very low complexity, polylog n complexity. Right. So we're a bit closer to our goal, right? So in this rigidity test and the sampling test, we can just swap out with this quantum low degree test, this QLD, and we can certify that Alice and Bob are really going to generate uniformly random n-bit strings that match.
So like you're actually generating like true random bits here.
Yeah.
Like you manufacture random bits out of nowhere basically from a small amount. Like it's not even pseudo randomness. It's just purely random.
Yes, exactly.
Okay.
So this is one really magical thing about these non-local games or these Bell tests. By having this assumption that you have these two players who can't communicate with each other, you can run some test with them, and the amount of randomness that you invest into this test is very small. Right, the seed randomness is only polylog n. But what you get out is going to be exponentially more randomness out. So, and yeah, it's information theoretic randomness. There's nothing pseudo about it. And in fact, this, I mean, not this specific test, but based on these ideas, people are actually trying to build randomness generation protocols. Did I mention this? Maybe, yeah, so actually, for example, in the United States, there's this government agency called NIST, which they set standards and so on. They actually have this thing called the randomness beacon, which broadcasts, U.S. government certified random bits, and supposedly the source of this random bits comes in part from these Bell tests. So, anyways, that was kind of an aside.
It's not quite that the randomness is coming from nowhere. I mean, it's coming from nowhere from the perspective of whoever is running the game, but the players still have to have, n EPR qubits.
Yes, I guess the point is that whatever randomness comes out of this experimental process, you're guaranteed by the laws of quantum mechanics that no one outside of your lab apparatus could have predicted that randomness ahead of time. In particular, Alice and Bob couldn't have known it before the, that their outcomes before the experiment too. So, even they couldn't have predicted it. So let's see. Okay, so now we get to this issue that Hugh brought up, which is, this is all great. We've reduced the complexity, but we still are not accomplishing our goal, which is to have Alice sample a uniformly random X and Bob sample a uniformly random Y that's independent of X. Here, X and Y so far are exactly the same. But it's really important in this original game GN that Alice and Bob don't know each other's random inputs, right? So the major problem that we have so far is Alice and Bob still each other's generated randomness. So we somehow have to get them to generate independent randomness. And not only that, but also guarantee somehow that they don't know through some other means, like they have no information about what other string the other person got. Okay. So we'll actually tackle this in two stages. So let's see. So what we'll do is, in this rigidity test, we'll have Alice and Bob play two parallel instances of this quantum low degree test. Okay, and when we do that, we will certify that they actually share two blocks of n EPR pairs. All right, so you can imagine what the rigidity guarantees of this would be. So the rigidity of QLDN guarantees us that, suppose that they pass this rigidity test with probability very close to 1, then we know that they must have 2n EPR pairs, and we can divide them into 2 blocks. So Alice has, well, let me draw it this way. So Alice has a block of EPR pairs. So does Bob. Okay. And they have a total of 4 possible total questions. So they have what I'll call TX1, TX2, TZ1, TZ2. And you can probably guess what this means. If any of the players get TX1, then let's say Alice gets it, then she'll measure her first block in the X basis and report the outcome. If she gets TX2, then she'll measure the second block in the X basis and so on. So, measure corresponding block in corresponding basis. Okay, so this is what we get from running 2 instances of QLD. And now we're going to start putting this together into what we call the introspection protocol, right? So the reason we call it the introspection protocol is because instead of asking the players directly, here are questions X and Y, why don't you ask yourself your own questions and then answer them yourselves, right? You're doing some introspection. Okay, so this will be the introspection protocol. Take 1, we'll do one final modification at the end. So in this introspection protocol, we have the rigidity test, right, which is to play 2 instances of QLDN. And then we're going to have the introspection test. Right, and here, what the verifier is going to do, it's going to ask Alice and Bob to, it just tells them, start introspecting. Right, so literally the label of this question is just introspect. There's no other data attached. Alice will send a pair, X and A. Bob sends a pair Y comma B back to the verifier, and the verifier accepts if in the original game, G sub n, dn of xyab is equal to 1. Right? So you basically ask Alice and Bob to generate the questions, answer them, send them all to us, and then we'll just verify that their questions and answers satisfy the original game. All right, so so far these 2 tests are not connected to each other, right? Because you know, Alice and Bob so far will know that introspect is very different from the rigidity test, so there's no reason to expect that Alice and Bob will introspect correctly. So we'll need to introduce an intermediate test that kind of connects the 2, that ties the 2 together. So here we're going to do what's called an Alice sampling check. Right, so we're going to ask Alice to introspect. So Alice will send a pair X comma A. Bob, on the other hand, we're going to ask him to, you know, to answer TZ1, right? So this TZ1 is a game from the QLD. Okay, so as far as he can tell, like he's either in the rigidity test or he's in the sampling check test. He doesn't know which. He responds with some string X prime. And then we accept if X is equal to X prime. Okay. And then Bob, there's also like kind of like the mirror version of this where we do like the analogous thing. You know, we'll ask Bob to introspect and ask Alice to measure TZ2.
Isn't X prime n bits?
Yeah. So X prime is n bits.
X is 1 bit.
X, here we're expecting X to be n bits.
Oh, okay.
Yeah, so let me write that down. All right, because that's what the original game expected X and Y to be n-bit strings. Okay. So let's see. Maybe before I describe what's going on here, any questions you might have?
So just to confirm, A and B are like the questions and X and Y are the answers?
Other way around.
Oh. Wait.
Yeah. Well, we have to be careful here because there's like lots of different games floating around. X and Y are supposed to represent the questions in the original game that we're trying to simulate. In GN. And A and B are supposed to be the answers of that, game. In this introspection protocol, we're putting all of them as answers of Alice and Bob, because they're generating all of this for us.
Right.
Yeah, good question. Let me draw, you know what, actually maybe this might help. So here's the original game GN. We have Alice, we have Bob, and we're supposed to ask them X and Y. They're supposed to respond with A and B, right? And then we compute d of x, y, a, b is equal to 1 or not. But in this introspection, the protocol looks a little different. So instead of sending X, we just send them a single command, intro, and they're supposed to send us both X and A or Y and B. And we still compute d of x, y, a, b equal to 1, right? Okay, so that's what this introspection protocol is supposed to be doing. Here's what we're hoping is being accomplished by this protocol. We're hoping that, let's see. So let me draw. Okay, and I'll just draw this as a picture. We're hoping that, by playing this rigidity test, we know that they're sharing these two blocks of EPR pairs. Okay, they might have this other entanglement that we can't characterize yet. So we'll just call it we don't know what it is. So these are the EPR pairs. This is the auxiliary entanglement. What we're hoping is that when we ask them to introspect, Alice will measure her first block using the measurement TZ1. Okay, she'll generate, when she gets this, she gets a uniformly random string X. When Bob is asked to introspect, he'll measure his second block using TZ2, and he'll get a independently random string Y. And then Alice, when she gets her question X, she's going to then go to her auxiliary quantum state and measure that using whatever strategy she would have used in the original game. Okay, so it's like a two-step process. First, measure these EPR pairs to generate your question, and then perform whatever strategy you would have done in the original game. Okay, so this is the intended process. Any questions? Does this make sense, or have I lost people? Okay, so we're not quite done yet because the protocol, this introspection protocol I described, doesn't quite certify that this really is the picture that's happening, right? This is, Alice and Bob could actually potentially cheat this and do something else when we ask them to introspect. So, and this is related to what kind of Hugh mentioned before. Does anyone see what might be the issue?
There's nothing preventing Alice from performing the same as Bob's measurement on her second set of EPR pairs to see what Bob's question was. And Bob can do the same.
Exactly. Yeah, so in the original game GN, the whole point is that Alice has no way of knowing what Bob's question is supposed to be. But in this setup, in this introspection setup, if she's really curious, she could just peek at her second block of EPR pairs, just measure them in the Z basis, and she would know exactly what Bob got, right? And this would be really bad because then we're no longer simulating the original game in a faithful fashion. So this is like the final problem in this question reduction that we have to deal with. So, the problem is that nothing is preventing Alice or Bob from measuring the second block to know what Y is. So this is so this would imply it's not a faithful simulation. Of the original game G sub n. Okay, so we keep on running into problems, but we're going to fix them. So the way we solve this problem is we're going to have Alice and Bob prove to us that they didn't get any useful information from the block that they were not supposed to read. Okay, and this is where we use the uncertainty principle. So in fact, not only do we ask Alice to, when she's introspecting, we don't ask her just to measure the first block in using the Z basis. We're going to ask her to measure the second block in the X basis. So actually, let me make a copy of this. Diagram. So we're going to ask her to measure this second block using TX2, and Bob is going to measure the first block using TX1. So she's also going to report an n-bit string called U. Bob is going to report an n-bit string called V. And here's the thing, so we can, with rigidity, we can know for sure that Alice and Bob are measuring these two blocks in the way we're asking them to. And if we know that Alice has measured the second block in the X basis, since X and Z bases are complementary, her string U is going to be completely independent and completely random and like U is going to not depend on Y at all. Okay, so she's going to, basically you can think of these extra strings U and V as like certificates of deletion. And when the, the verifier can check that these certificates of deletion are correct, and the verifier will then be confident that when Alice generates her question, her answer A, using this auxiliary state, that her answer A depends only on X and does not depend on Y at all. And the same thing for Bob. So, the solution is to just have Alice and Bob measure their forbidden blocks in the X spaces. Right, so maybe it'll be a good time to take a break since this has gone a little long. Let's come back at 5:18.
Henry, you're muted, by the way.
Oh yeah, I was just pre-writing stuff.
Okay, okay.
Yeah. I guess it's 5:20. Yeah, I guess I could have just done a silent lecture for the remainder. Okay, so yeah, I'm just sort of sketching down what this final introspection protocol looks like. You know, we do the rigidity test, which is like this QLD. We do the introspection test, right? So Alice and Bob are both told to introspect. They now report a 3-part answer, right? So Alice reports X, U, A. Bob answers, let's call it V, comma, Y, comma, B. And then the verifier is just going to accept if X, Y, A, B is equal to 1. Right? But then we need all these other, you know, we need to check that X and U and V and Y are done correctly. So we have the Alice sampling test. Right, so Alice is told to introspect as usual. Alice answers X, U, A. Bob asked, he's asked T, Z, 1, T, X, 2. He answers with X prime, U prime, and then the verifier accepts if X prime equals X and U prime equals U. And then there's also a similar Bob sampling test. So this is our introspection protocol. And this is what we wanted. So first, let's check that we've really reduced the sampling complexity, right? I mean, where does the sampling complexity come from? Well, it's dominated by this rigidity test. And we're promised that is polylog n, right? Like in these other tests, the questions are just labels like introspect or TZ1, TZ2, TX1, TX2, right? So that's just you know, 5 more questions that are added. So overall, the sampling complexity is quite small. The decision complexity hasn't been reduced at all because the verifier is still performing, you know, computing this dn xyab. That's really going to be the dominating computation that's being done by the verifier in this decision process. And that takes, you know, n squared time. So, but we'll handle that in the next phase. Let's see. So we've argued that we've reduced the sampling complexity, and hopefully it should be intuitive why this game captures, you know, simulates the original game G sub n. So you know, what we have is that, you know, suppose that the original game had a perfectly winning strategy, then so does this introspection game. And that's because Alice and Bob can just honestly share these EPR pairs and just, you know, perform this perfect winning strategy for the original game in this introspection phase. So overall, they'll just win with probability 1. Right, which is what we wanted. So if the original game had value 1, then in this introspection game, let's call it G intro, it also has value 1. right? What about the converse, right? Suppose that in this introspection game, the players won with probability 1, or they had a perfect winning strategy. Then does that mean that the original game had a perfect winning strategy? It turns out yes, right? Basically you rely on the rigidity of QLD in order to deduce that. So the converse is also true. Right, so we've preserved the game winning behavior, but with smaller sampling complexity. Any questions about question reduction? Okay, so let's go to the second part, which is now we need to reduce the decision complexity. Okay, so here we can just sort of abstract out things and not really worry about the details of this introspection protocol. All that we're going to assume is that that we're just given some game. Okay, I'll still call it G intro N, but we won't really use the fact that it's an introspection game. That has, short question complexity, and n squared decision complexity. And we just want to reduce the second part, and then we'll be done. So the main idea is that the verifier, instead of performing all these decision computations itself, it will, again, offload it to the players. And the players will prove to the verifier that they've performed these computations correctly. And this is where we use PCPs, these probabilistically checkable proofs. Okay. So how are we going to do this? Again, let's draw these two worlds, right? So we have G intro N. We have Alice and Bob. We have the verifier. And in this G intro N, the verifier is going to send some questions X. Okay, and here X is going to be unrelated to the X's that we've been talking about. Like here, the X's are going to be short, right? These are the short questions X. Alice is going to respond with some answer A. Bob responds with answer B, so on. One kind of conceptual difficulty to applying PCPs is that what do we want to prove, right? Like so the goal is we want the players to prove to the verifier that if you were to compute D of X, Y, A, B, that the output would be 1. But one conceptual barrier to this is that neither player, Alice or Bob, they don't have all of this information, right? Alice only knows X and A, and Bob only knows B and Y, right? So so each player by themselves cannot compute, they have no idea whether this statement is true or not. Right, so one issue that okay, so we're going to have to do something to first fix this issue. And this is where we use something called the Aracularization Transformation. Okay. And it'll seem kind of crazy at first, but maybe I'll convince you that it's not such a crazy idea. So in this, we're going to create a new game. Let's call this G Arac subscript n. And in this new game, Alice, instead of just getting the question X, she'll now get questions X and Y. Right, so let's draw it this way. Right. And I won't say what Bob's going to get. And what Alice is supposed to produce are answers A and B as if she were actually both Alice and Bob. And just to actually, because it's kind of confusing, in this Aracularization game, I'll label the players P1 and P2. Okay. So we should think of P1 as saying, look, you're supposed to play the roles of Alice and Bob. Okay. And this would seem kind of counterproductive because now there's no, now there's this one player who knows both questions. Right? And that shouldn't be allowed in a non-local game. Right, and by itself, this seems problematic because, how do we know that these questions don't depend in some complicated way on both of these questions? Both of these answers, A and B, depend in some weird way on both X and Y, right? So this is where we're going to use the second player, P2, to kind of enforce that A only depends on X and B only depends on Y. And so what happens is, sometimes with P2, we're just going to send them a single question. And they respond with an A prime. And then we'll just check consistency between A and A prime. Or P2 gets Y, and they're supposed to output some B prime. And we check consistency with B. Okay, and what's the point of this this game is that here we know that A prime for sure does not depend on Y, right? Because P2 only gets X, let's say in this case. So if A prime happens to agree with A in this setting, then by transitivity, we know that A cannot depend on Y either. Sorry, that was not, does not depend on Y. Okay, so in this new game, what is the verifier doing? It's going to say, here P1, please hear both the questions X and Y. Give me both answers A and B, and I'm just going to first check that X, Y, A, and B would have satisfied this G intro game. But just to make sure that A and B only depend on the questions they're supposed to, I'm going to use the second player to keep you honest. So the verifier checks, that D intro, whatever the decision procedure is supposed to be, of D X, Y, A, B is equal to 1. Also, with some other probability checks, consistency between P1 and P2. So does this step make sense to people? Or any questions about this? I should say what I'm claiming about the claim is that, well, I guess there's two parts to it. One is that if the players are winning well in this oracularized game, then it must have meant that there was a good strategy for this original intro game. Right. And I won't explain how you prove this, but basically, you can imagine that if it's passing all these consistency checks, we know that this P1 is really, generating A based off of X only, and P1 is generating B off of Y only. And so that counts as a strategy for this intro game, right? That's winning well. The other part is, how do we know that it's possible to win this oracularized game with good probability anyways? And actually, this is not always true. What we require is that if G intro has this word I'll have trouble pronouncing, but oracularizable strategy, if G intro has an oracularizable perfect strategy, then there is a way to win this oracularized game with probability 1. So this might sound tautological. I mean, it kind of is. But the point is that there's some property of this strategy that allows us, allows the players to, succeed in these consistency checks. Okay. Maybe let's just treat it as a black box for now. But the important thing is that in all of the games that, each of the different games that we're considering in each of these little transformations, it will turn out that they're all oracularizable. Okay, so it's just some technical assumption that you'll need. So this property is satisfied by all the games considered here.
Can you maybe give an example of a game that's not oracularizable or whatever? Like, I can't even think of one that wouldn't be.
Yeah, well, maybe let me say why you need a condition in the first place. So let's take the, now let's do it this way. So let's take the CHSH game. So I think this is a good example. So I believe it's not Aracularizable. Why not? Because in the CHSH game, right, like the players are supposed to measure their EPR pair in using like X and Z, right? But you know, imagine that Alice is told to measure in the CHSH game like the Z basis, and Bob is told to measure in the X basis, right? So this would, I guess, would correspond to questions 0 to Alice and 1 to Bob. Now, so certainly, if we were to try to oracularize this, P1 would get 0 and 1. And what would P1 try to do? To try to mimic the behavior of Alice and Bob in the CHSH game. We'll say, oh, I'll just generate like an EPR pair and measure, you know, one half of the EPR pair with Z and the other half with X and give the answers to you, right? That would be fine. But the question is, P2 is left out in the cold. Like P2 has to generate some A prime that matches P1's A, but it doesn't, you know, what entanglement is it going to share with P1 to get this consistency to happen? And I think for this example, it's not really possible. Right, so basically you need yeah, I don't know if I have a good explanation of this, but basically Aracularization says that this issue doesn't happen.
Yeah. Can I ask a quick question?
Yeah.
Could you scroll back up to where you drew the GN intro?
Mm-hmm.
Yeah, right here. Shouldn't, if this is GN intro, shouldn't the verifier just be telling Alice and Bob to introspect, and then they return A and X and B and Y?
Yeah. Yeah, I guess this part
playing the game. Like that's just
right.
GN, right?
Yeah, so I guess this is confusing. Here, X and Y are, I'm overloading it. So I guess in this answer reduction step, I guess what we should just sort of like unload everything we've learned about the introspection game, such as like what you just mentioned, and just treat GN intro as just some given non-local game where the questions are labeled X and Y, which if you unwrap it, X would correspond to introspect and Y would correspond to introspect or something like that.
Okay.
Yeah, so I'm just trying to abstract away from all the details of the previous section.
Okay.
Yeah, so I guess that would be kind of confusing. So, oh, also this should be the intro. Okay, so maybe I'll write the note. X, Y, A, B. Oh, okay, well, that'll just end up being more confusing. Okay, so with all this stuff about Aracularization, the point is we've set ourselves up in the way we wanted to, because now one of the players has all the information that is needed for them to prove to us that the verifier in G-intro would have accepted. Right? So now we can sort of just focus on P1. So here's step 2. And again, I'll just keep on drawing pictures. So here's P1. P1 receives X and Y. simultaneously, and it has some process for generating A and B. And we have a way of checking that, again, A only depends on X, B only depends on Y. So P1 generates all of this, but as the verifier, we're too lazy to compute this decision D intro X, Y, A, B. So we're going to ask P1 to provide a probabilistically checkable proof that of the statement D intro X, Y, A, B is equal to 1. So P1 will prepare a PCP of this fact, if it's true. I mean, if it's not true, then P1 will just do something, but because it's a probabilistically checkable proof, we will be able to verify whether it's a correct proof or not. So what does a proof of this look like? I mean, I won't go into the details, but just diagrammatically, we can imagine that P1 will output some long string that's called pi. This is the proof. And the verifier won't read the whole string. The verifier is just going to choose 3 random locations of this proof, 3 random bits. So choose I1, I2, I3. And based on those 3 bits, the verifier will accept or reject. And if the verifier accepts, then with high confidence, the verifier will know that indeed this D intro of XYAB was really 1. And all of that would have been, and then how much work is the verifier putting in to do this verification? It's something very low. So the verifier in this PCP only uses polylog n time to choose these locations and check the answers. Okay, so if D intro of XYAB is really not equal to 1, then with high probability the verifier will reject. Okay, so that's kind of the really high level. There's a lot, actually, there's like a ton of technicalities that I'm like sweeping under the rug. For one, like I said, that this P1 will prepare this long string that the verifier won't read in its entirety. Actually, that's technically not legal in the, we can't assume that. So not only, okay, so not only does like the complexity of, like the complexity of this decision process have to be polylog n, but we also have to insist that all the answers are only polylog n bits long. Okay, so there's extra stuff that we have to do to make sure that this works, but let's not get into it. The main point is that here we're just doing something that's purely classical, which is just to prove this computational statement, right? This dintro is just a classical computer program, right? There's nothing quantum about it. And we really just need to just efficiently verify that, this computation would have accepted. Okay, so what's the punchline? Using PCPs plus this Aracularization procedure, verifier can, in polylog n time, check basically whether the value of G intro n is equal to 1 or not. And so we've basically arrived at our goal. The output of this compression procedure will be this, this thing that does this PCP checking. Decision complexity is polylog n. Sampling complexity is also polylog n, which is our final goal. Okay, so that was probably not, there was probably lots of that was pretty confusing, but despite that, any questions that you might have?
Back in step 1 in Aracularization.
Mm-hmm.
When you say or, when P2 does these two things, when you say or, do you mean like you flip a coin and you choose one, or do you mean, okay, so you do flip a coin, okay.
Yeah. Yeah, so I guess it's with probability 1/2 either.
Right, I see.
Yeah, good question.
Just a good question. Is usually just 2 questions and 2 answers, or like X and Y, or could you have X, Y, and Z here for these games?
Yeah, you can. I mean, here we're just considering 2-player games, so that's why we have X and Y. But I imagine you could also, there is a, there's a 3-player analog. I think things might get more complicated there, but you can certainly define it. Yeah.
Okay. And this is when you say it's a polylog, it's logarithmic in the number of players, I guess. Huh?
No, the polylog here is in n. N is the index of like the game. So we have these games like at the very, very beginning we started with this sequence of games G1, G2, Gn. Yeah. So that's the n we're talking about. Yeah.
Okay.
Yeah. So anyhow, just stepping back, like this is, now you have some glimpse of like the ingredients that go into proving this compression theorem, right? We basically used, all the tools, many of the tools that we've talked about in this class, right? Like PCPs and like verification and rigidity and nonlocal games and the uncertainty principle, really to squeeze down the complexity of each of these games. And using this compression theorem, we can get this reduction from this halting problem, right? And we get all the consequences of that we saw last time. So you know, this basically, you know, wraps up our discussion of MIP star equals RE. Yeah, you know, I think it's kind of interesting how really all these different ideas from, you know, rigidity comes from like, you know, non-locality, right? Like the study of Bell tests and quantum physics. PCPs comes from just classical complexity theory, and you know, it all connects together with, you know, this stuff from mathematical physics and pure mathematics that we saw last time. So that part is certainly very interesting. And I don't know, I think of what it hints to is really all of these are pointing to some more, you know, central or general phenomenon that's sort of common to all of these different fields. You know, what that phenomena is, I'm not exactly sure, but you know, I think you know, it's something that people are trying to figure out. Yeah, so that's it for this section. And you know, so the last class next week, we're going to, you know, to put aside, you know, talk about something completely different, and we'll talk about this QMA2 complexity class, which I alluded to, maybe that's 5 or 6 weeks ago. And this is about, you know, we've focused a lot on the power of entanglement, but QMA2 is really an exploration of the power of unentanglement. So, so we'll finish with that. All right, so thanks a lot, you guys. And yeah.
Can I ask a question?
Yeah.
So maybe I missed it, but why is it, like, why are we allowed to assume that all the games we're considering are ocularizable?
Yeah, Aracularizable. Why are we, it just, yeah, if you open up all the technical details, it turns out that they have this property. So, you know, if you input a game that is Aracularizable, then each of the steps preserves it. So you can always just assume that it's like an invariant that's maintained.
Okay.
Yeah. Question. We'll stop recording.